So in the previous class, we started to look over a more complex Jupyter notebook, which we had worked with the empty cells or the null ones. We understood when they are in the dependent variable, we drop those observations. When it's on independent variable, for categorical variables, we did mode imputation. And for numerical, we did median. So we did all the way to take care of all of the missings. And here, I just go a little back from imputation part. So, sorry, from the encoding part. So some of your variables are categorical, and you cannot just put in the models. All of the categorical variables should be converted to numerical ones. I've talked about two different ways. One way was label encoding, which you assign a number to each category. We said that it's better that there's an order between the categories, but sometimes there's no order. Like, for example, for 6 or the embarked port doesn't have, there is no order between them. So anyway, for label encoding, we assign a number to each category because we should have a one way to use it in our models. Second one, doing one-hot encoding. Basically, you make a dummy variable for each category of your string variable. So having said that, we import vector assembler for making the feature column. You might remember that the format that you need to enter your data into machine learning algorithm is you make a feature columns that is a list of other columns. Vector indexer for making label encoding. One-hot encoder is for making one-hot encoding, and also a string indexer. So as you see, for 6, with the string indexer, we make a label encoding and change 6 to 6 index. So, but for one-hot encoding, we change those. We make dummy variables out of 6 index with one-hot encoding, and we assign it to a vector of 6 vec. So basically, 6 vec means collection of dummy variables created for 6 variable, and same for embarked and P class. Basically, 6 index is the label encoding variable, and the variable's name vec means a vector, or basically a collection of dummy variables created for the categorical variable. Also, keep in mind here, when I run this block, it runs fast because here I just define indexer and one-hot encoding objects. So here you just do defining, it didn't run it. Similar to the previous one, we make a vector assembler object. So as you see, for one-hot assembler, we just select the columns that are one-hot encoded. For label encoding, I'm selecting the columns that are label encoded. For example, as if embark vec versus embark index. Then we make a columns of feature out of the list of the columns that we want to do. Also, I'm importing logistic regression and random forest classifier from PySpark machine learning classification. You have seen that maybe we can use NumPy package very well. Also, pandas is doable, but you know, scikit-learn or sklearn is not developed, or is not completely applicable within Spark environment. That package was created mostly for standalone computing. So for maybe later, it will be further advancement in scikit-learn and make it more adaptable within the Spark environment. So doing machine learning in Spark has some limitations. The codes are very similar, but you are not as flexible as scikit-learn. So you don't have that much of different objects or functions that you can create. So for today, I'm importing logistic regression for test and train, and also random forest classifier for feature selection. Also, here I do some of my calculation by defining a pipeline. Pipeline just means steps of procedures that you want to do over a data frame. So you define the steps that you want to do. If you look at this link, which is a part of your reading assignment, you can get to the Spark pipelines, and it gives you some explanation. Basically, it's very easy. It has some section, one of them data frame. It just means the data that you want to use. Estimator, a good example of estimator is a machine learning algorithm. Basically, you estimate or train some algorithms over your data. And with transfer method, you just apply those estimator. So you make an estimator or train an algorithm, and with transform, you just apply it. Also, pipeline just means a chain of multiple process or steps that you want to do. Those steps could be a transformer or estimator. And it has some parameters. So as a part of your reading assignment, please go over this pipeline page. It gives you further explanation and also has a very good Python example that you can do step by step and understand further about pipelines. But as a summary, where's that? As a summary, we just first define the steps, and after that, we create a pipeline saying that which steps we want to use. So you have seen here, for example, I had one-hot encoding and label encoding. If I want to do one-hot encoding, I should have both of the steps. I should have, first I should do apply a string indexer, then apply one-hot encoder. But if I want to do label encoding, I don't need to use these steps. So as you see here, I define a pipeline for LR stands for logistic regression and one-hot encoding. I'm just saying that the stages are first applying the indexer function, then applying one-hot encoding functions, then making I'm doing one-hot encoding, and finally training a logistic regression, which I define here. So in that step, I take a feature column and survived column as a label column and train a logistic regression and also a random forest. I define another pipeline. In this pipeline, I don't have those steps. I don't have encoding steps because I just want to do, I just want to do label encoding, not one-hot encoding. And for random forest, I also don't have the encoding steps. Basically, here I want to have 3 experiments. First, I want to look at the performance using one-hot encoding. Then I want to check label encoding. Then I want to use random forest for feature selection and see what happens. So these are the 3 scenarios that I'm going to do in this class. Usually, you don't define them, all of them together. Maybe first you do one-hot encoding and go to the end. If you don't like the performance, which I mean accuracy or AUC, you go back, you use this pipeline, then define this pipeline. But for today, I just define them all of them in one step because because I know what I want to do for today, but it's not usually the way that you do. And whenever your code is that much small, maybe defining pipeline doesn't have that much of point, but maybe for class project that you have several steps, maybe you define several pipelines and you want to check different scenarios. Having pipelines helps you to more organize your codes, because you have like hundreds of lines of code, and sometimes it's very hard to just go back and find them. So with a pipeline, you can make it more organized.
So is pipeline a qualitative thing? Like it helps you make it. So basically, pipeline is something that can be that is used to build a process.
Yes.
But I just don't understand this thing. Like there is a variable named pipeline, like there is a function named pipeline.
Pipeline just means
like how are we using? Why are we using this function?
Basically, this is the way that you define. You let Python knows that you have some steps.
Okay.
So Python knows that when it says pipeline, it just means you are going to define some steps, but you are not running here. It's just for defining.
So then what is the benefit of defining?
You just want to make it more organized. So later, if somebody read your code, they won't get confused. They understand this is the pipeline. This is the process that you did. It's just some kind of a better communication. So later in your project, I don't need to just go back to check all of the blocks one by one and memorize them. I just can say, okay, what are the steps that you followed? It just shows the flow of your processes. When your code is very small, like here, you don't need to make pipeline because you can easily understand what is going on there. But when you have several steps and you try to improve the performance in many ways, so I instead of just memorizing all of the blocks that you did, I just look at your pipelines and see what you did. It's not necessary, but it helps you to more organize it. And when you have a very large project, you can understand it really helps for organizing. Same here, let's look at this one. So in this block, I divide my data into two sections of train and test. And I just said train 80%, test 20%, random seed 110. The way that is split is randomly, or very close to a random process. But every time my result might be a little different, which is fine. But for reporting purposes, you want everyone who runs your code get the exact same result that you got. So I assign random seed of 110. So every time that I run it, I get exactly the same result. So as you see here, I'm fitting my pipeline over train underlying Titanic. Can you guess, is it the estimation process or transforming process? Why transform? I mean, it's very hard to say, frankly speaking, now, but let me show it to you. Here, you're just training an algorithm. You are not changing your data frame. Whenever you change your data frame, is a transformation process, or you doing transformer in the pipeline. Here, with fit method, I'm just training algorithm here, the logistic regression over my Titanic dataset. Now it's actually running. As you see, it takes a little bit of time. So I'm estimating or training 3 different models. One of them, one-hot encoding, and using logistic regression. The second one is label encoding and using logistic regression for training. And the last one is random forest over labeled data. And I use it for feature selection later. Here, now I'm doing transformation. So I already trained a model with the fit method. Now I'm applying over my train and test set, which either one-hot encoded or label encoded, as get the predictions. So let's see what happens. So we had two different pipelines for one-hot encoding, label encoding using logistic regression. For evaluating the performance of my prediction, I'm importing binary classification evaluator for AUC and multi-class classification evaluator for accuracy. Then same as other project that we did, first we need to make an object of AUC and an object for accuracy. So as you see here, with binary class classification, I'm just saying that my raw prediction column is within prediction, and label column is survived. Use it for AUC. For accuracy, is the steps that you need to do. First, you call multi-class classification evaluator, then define prediction column and survived column. Let's look at one of the prediction. For example, in test set that you did label encoding, let me exclude this column. Dot select. Dot select means just show these two columns. I want to as you see, it has the variables that I used: feature column, raw prediction, and probability. So can anyone say what is the difference between raw prediction and probability? My raw prediction is between negative something to positive something, and probability is between 0 and 1. So the raw prediction is basically the output of the logistic regression. It's between -1 to +1, but but if you want to get probability, there is a formula how to convert the output of the logistic regression to probability. You can check logistic regression formula. But anyway, at the end, look at the probability column. If the probability is more than 0.5, like the first three, the class is 0. If it's less than 0.5, the class is 1. So because the default threshold is 0.5, so if the probability is more than that, class 0 is less 1. And if you go to the documentation of this algorithm, you can change the threshold. So you can put 0.6, 0.4. And AUC, if you might remember, just shows if you change the threshold, what will be the arrow under the curve. So anyway, here we define objects for accuracy and AUC. And here we just evaluate our results over the test and train of label encoding, test and train, one-hot encoding, both for AUC and accuracy. So for accuracy, you should put this parameter, just your evaluator understand that needs to calculate accuracy. With that function, you can get other parameters too. Let's check one-hot encoding first. So in one-hot encoding, I'm looking at the test set, AUC of test set and train set. So AUC of my test set is 0.69 and train set is 0.79. So do you think what happened? Is it a good performance, bad performance, or?
Actually overfitting.
Why overfitting?
Because the test accuracy is much lower than.
Yeah.
I think it's good. Maybe like there might be few outliers in the train, and they are not like much outliers in test, and that's test is giving the right accuracy.
Yeah, you guys might write another one. Maybe you use too many variables. So maybe you make it other pipelines and just go back, check some part. Maybe you put a part for taking care of outliers, or you add a section for feature selection. So as I said, data mining project is a cyclic process. You go through the evaluation. If you don't like it, you go back, change some parameters, then go forward. Yeah. Interesting. So yeah, I mean, it might be because of we have too many features, and when you have too many features, it might not only ruin your prediction, it also might cause overfitting. It means your model fitted very well over train set, but it's not good in the test set, which is bad. We want to generalize our model for future prediction. Then check the accuracy. Again, accuracy of train and testing one-hot encoding there's a big differences. Again, a sign of overfitting. And here, I'm just trying to do same performance check for AUC. As you see, the gap is much less. It's like it's close to 4%. And for accuracy, is about less than 3%. Since it seems that label encoding is more generalizable, although one-hot encoding is more intuitive, in label encoding, we just assign a number to each category, but worked better than one-hot encoding here. It's not necessarily the case always, but here label encoding works better. Yeah. So another step, we might do feature selection. See if we do feature selection, does it help or not? Sometimes it doesn't help, sometimes it helps. By the way, feature selection in PySpark is much limited than scikit-learn. So you don't have that much of algorithms or approaches to do feature selection. So one of the, I think just two ways that you can do feature selection in PySpark. One of them is just random forest. So I already trained a random forest over train set. I can look at my random forest prediction and take out the most important variables. Because when you use variables, some of them turn out to be more important by model. Maybe we can use it for training and logistic regression. Let's see if it helps or not. There is no guarantee that feature selection always works. So your random forest prediction has some outputs. The way that you can get feature importance is just by this function. So you add a stage bracket -1 and feature importance. You can look at the prediction later, and it gives you several outcomes. And also, if you check the PySpark documentation, it just show you how many or what kind of output it gives. It's one of them is feature importance. As you see, it gives you a dictionary with some index and importance value. If you check the columns, you can understand, okay, 0 means P class index, 1 means sex index, maybe 2 means age. You can either do manually. For example, you can manually look at the importances that are more than 0.05 and pick them, or you can do it automatically. Both of them works. So first of all, I transfer my train set to a new data set. And I define a function here. It's a very complex one. I recommend later just go step by step. In scikit-learn, you don't have to define a function. You can easily get the importance. But here, I mean, it's more intricate steps. Basically, there's nothing. I just look at the column names and also look at these IDs and just assign a name to each IDs. Again, you don't necessarily need to make a function to get that. You can easily just look at the column names and IDs and just pick the names that are associated. So by running this function over the feature importance dictionary, your data frame that predicted, and as defining the label column, you get this data frame. So names, if they are categorical variable, the categories. If they are numeric variables, you don't have categories, so there's none over there or null. And the importance here. As you see, what is the most important variable in predicting survival here? If you look at this data frame, yeah, 6. What? Because the importance is 0.55. The least importance is the port that they are embarked. What's your question?
What is this 0.55 or 0.14? Is it probability or is it some kind of confidence interval? Is it correlation accuracy?
You can. There is a formula for calculating importance, by the way, but it just shows the weight of each variable in prediction.
Like what will the 0 to 1 or minus 1 to 1?
0 to 1.
0 to 1. I want to say it's correlation, right?
It's similar. Conceptually, yes, there is like it's just kind of, could you consider as a correlation, but it's not correlation. Because in correlation, higher correlation to dependent variable means maybe a better variable. In that concept, there's some similarity, but the formula that for making correlation and importance are different. So here,
one more thing.
Okay.
Like why numerical variables have less score? Like, is there any kind of a particular reason that or is it just a formula that they're getting?
Actually, machine learning was kind of black box, but it turned out to be less important. I don't have any reason for that. Maybe if you go in depth, you see that the age is not that much different. So the people who survive, you have so many, I mean, a wide range of age. Maybe if the very young people survive, you have more importance because it shows the age could be important. Or maybe age-wise, maybe the people who survive, they are in a wide range of age or price. It could be a description of maybe what you can do. Actually, is a really good thing. Your question is usually really good. So maybe one of the ways after prediction you get the label, just check what happened to people who survived. Check the range of age, fair.
Maybe their entire statistics, like me more.
Yeah, you can check that and see. That could be a reason. But this is a black box model. I'm not very sure that could be a reason. Another one, look at fair and class index, P class.
Yeah.
Both of them are almost talking similar thing, right? So fair means if the higher class, more expensive. But as you see, one is very important, another one is not very important. It happens even in statistics when two variables are correlated. Basically, when you want to do regression, one of them turn out the t-test of that variable, one of those correlated variables might be very low. So in statistics, we have something similar. So we try to not to use correlated variable because one of them turn out to be not significant. Similar might be here. But for age, I don't have any reason. We might look at the people who survive and not survive and look at the distribution of their age. Or maybe port embark into shouldn't be important because it's just a city that they get to the ships. So it could make sense to be less important. But for number of children, parents, and siblings, maybe we need to look at the dependent variable of test and train and see if there's a meaningful difference or not. So anyway, here I'm also adding survived variable because it's just a feature, and for new prediction, I also need to have dependent variables. So it's the variables that are used for prediction after feature selection. I took out the ones that has the importance more than 0.05 and convert them to a list, because later I need the names to be in the list format to be able to make a feature column. So here I'm showing one way of using previous prediction of pipelines. It's not the most efficient or the best way, but look at here. So I need my variable to be in the index format, in the label encoding format. So what can I do? I already had a pipeline that I did convert to the label encoding, and I can use the previous model to here. I don't need to again convert them to the labels. So what I'm here saying, I already fit a model over my train set. I can select the variables that I needed. And as you see, I fitted a label encoding model. I just want to select the variables that I need. It's not the best way. Maybe you can make a new pipeline, new steps, but here is just one way of doing that. It's not necessarily the best way. I just want to show you how to use some of the previous works that you did. So here, I'm turning a logistic regression over my features column that is made over the selected variables. As you might remember, in the assembler, you use it for making feature column. And I apply for, again, train and test set. With the fit method, I'm fitting the new logistic regression with new features over my label encoded data. Let's look at the performance of the fitted model. Here I do predictions. So with the new model, with the new feature, I do the prediction. As same as before, I evaluate the AUC and accuracy in this block. And now let's look at the performance of AUC and accuracy. As you see, after doing feature selection, AUC of my test set is more than trained, which is doesn't seem great. Also, the gap between accuracy is now more. So previously it was less than 3, now it's about 4% differences. So feature selection not only didn't improve, also make a wider gap. So didn't work, sometimes it works maybe. So maybe you can make another pipeline for label encoding and feature selection with random forest and see what happens. So these are like, each pipeline could be like a cycle in the QSPM that you go back and forth and see what happens. In the one of the next classes, I do let's say fold class validation, like 5-fold, 10-folds. Usually, when your data is too large, maybe it's not very a good idea because you need several computations. But it brings you further confidence that you can generalize your data. If the predictions, if the performance in each fold and the associated test is similar, maybe you are more confident that you can generalize your model for further analysis. We do it later, but again, when we have a very large data set and you randomly split in train and test, maybe it's enough. Any question about distributed notebook? No question? Okay. Yes?
I'm still confusing about what is the difference between one hot and a dummy.
Okay, let me show it over my whiteboard, but if you look at the previous class video, I already explained, but let me just briefly explain here too. So let's talk about embarked variable. It was 3 different portal, I think E, S, Q, I guess, or C maybe. In label encoding, you say this is 1, 2, 3.
The difference between one hot and a dummy, not what was labeled.
Same.
The same.
Yeah, one hot encoding means you make dummy variable for each category. Same. So let's talk about clustering. So do you guys remember what this clustering means?
Yeah, it's proprietary.
So
Low level, and then you have to divide into different classes.
yes, in clustering, you at least you don't know the label of your test set. You might know the label of train set, but you don't use it even. So because in future you don't know the label, you just look at your observations and classify them in categories that are more similar to each other. And one of the most famous algorithms is k-means. So let me give you an example. So here, how many clusters you might have?
3.
So why not 2?
Maybe 2.
Why not 4?
It depends on, like what kind of a range maybe, or maybe what kind of clusters you're trying to build.
Yes. Here, maybe with your bare eyes, since it has just 2 dimensions, for you making 3 or 2 is more sense. Makes sense. For example, 3, this 3, or 2. Two is even more difficult, maybe. But we want to have a measure to see which one is better. So in k-means clustering, first you define how many clusters you want. Let's say 3. So what does k-means do? It just find 3 locations as a center of clusters that have closest distance to each observation within the cluster and has high distance to other observations out of the cluster. For example, if I say 3, maybe one center could be here, 1 here, 1 here. So the distance to this cluster, this observation to this cluster is much less than this, much less than this. And same for other observation. The distance of each observation within the cluster to the center is much less than other clusters. So you might say it seems a good cluster. All of the points in each cluster has a short distance to the center of the cluster and a long distance to the other centers. Okay, let's assume this is my new clusters. I have 4 clusters. Do you think it's a good clustering or not? Why?
All red should be organized together, all dark black will be organized together, or all circles should be organized
Yes.
together.
What you mean, I guess, means the distance to the center of the cluster should be less. For example, look at, let me just delete this one. Distance of this point in another cluster to here is much less to its own cluster. It doesn't seem to be good. And maybe one other point. Here, distance to its own cluster center is much more than the neighboring cluster. In 2 dimensions, you can easily see that. Well, even in 3 dimensions, you still can imagine. But let's say you have 7 different variables, 7 dimensions. Our eyes cannot catch it. It's very hard to say when you have more and more dimensions. One of the tests or parameter that you can use for similar concept is silhouette coefficient. In silhouette, if your silhouette coefficient is actually between -1 to 1, if it's 1 or close to 1, means all of the points assigned to a correct cluster. If it's close to -1, means some of the points didn't assign very well. Like here the silhouette coefficient should be close to -1, because for me, this is, at least here, maybe this is the right clustering. So when your silhouette coefficient is close to -1, means you have your points are not assigned correctly. If it's 0, means some of the points are in the border. Like, let me see. Okay, let me change this one. Let me put it. Okay, this point. This point has almost similar distance to both of the center. Because this distance is similar to this distance. So when your silhouette coefficient is next to 0, means some of your points are kind of in the borderline. It could be assigned to this cluster or that cluster. So it helps in clustering problem. So you do clustering, but you should define how many clusters you want. You might have some ideas and guess, but your guess may not be correct. So what you do, you define several clusters, and as a range, maybe you say I want to try 2 clusters to 10 clusters, and see which one has the highest silhouette coefficient, and consider it as the best number of clusters. Any questions so far? In scikit-learn, you have other coefficients, but again, number of coefficients in PySpark is a little limited. So PySpark is not very great in machine learning, but it's very great to work with a very large data set and also a stream of the data, which we talk it later. For example, a stream of tweets, a stream of comments. So for continuous interval of data, PySpark is really good. But in machine learning, it doesn't have that much flexibility or that much of options that you have in scikit-learn. In future, I mean, so you need to keep yourself updated. Maybe in future they put some more options that are available in like scikit-learn or as we call it, sklearn. Okay. Please, okay. I give you a couple of minutes to open the clustering experiment Jupyter notebook that I put over Moodle, and also you need to download and upload seeds underlying data.csv. That's the new data set that I provided on your Moodle. So in this experiment, we have data of 3 types of seeds. They are Comma, Rosa, and Canadian. So our train set is already labeled, but we want to do clustering to see if it's actually we have 3 clusters or maybe more. Maybe this Canadian seeds should be divided in 2 more types, Canadian 1, Canadian 2. Maybe Comma and Rosa should be merged in 1 category. So based on the seeds information that provided in data dictionary, we can run clustering, see based on their characteristics, could we define more clusters or less clusters? And we have silhouette coefficient, by the way. So the variables are area, parameter, compactness, length of kernel, width of kernel, asymmetric coefficient, length of kernel groove. So if later you work in your company or in research later, if you work with the Spark, just keep updated, but they promise to provide more machine learning options. But again, the reason that you use PySpark is not for doing high-end machine learning algorithms. It's for learning how to handle large data sets, one of them just being large or be a continuous data. Again, we import Spark session, we import k-means, and let's look at the descriptive statistics of the numerical variable. Here, all the variables are numerical. If there are some that are not numerical, don't see them here. Looking at their count, there is no empty data, so we can work with that. There's no null. Also, the means, standard deviation, mean, and max. Do you see any issue that you can find here? Is it fine? If there's some outliers, maybe we just need to drop them or change the values to null and impute them.
see the first one?
Area. Actually, here is very hard to find any issue because you need to have some background knowledge in farming. So most likely in future, either in research or in the industry, you don't know the background knowledge. Or as you know, the first step in Christian, knowing about the business that you're working. So in such a case, you need to work with people who have the background knowledge. So they might, in healthcare, maybe physicians, in finance, maybe people who studied finance, or in farming, people who do farming. So you can get their help for the first step that you do data preparation and also the conclusion that you make from that. Here, we don't find any issues, so good to go. Okay, here, again, similar to previous one, we need to merge all of the columns into one column of features to be able to enter into the machine learning algorithm. So I call vector assembler, and I use all of the columns. So data columns, we have 7 columns or 7 variables associated to seeds information, and I merge them into features. Also, I'm doing scale and centering my data, basically normalizing your data. Sometimes there's a high variation, or you don't want to change the data in the standard format. No. So for this reason, I'm importing a standard scaler and scale my data using with the standard deviation. One of your reading assignment is understanding what does standardization means. So I provide the link, so please study that. You don't have to submit anything, just read those documents about how to standardize your data. Sometimes it works, sometimes it doesn't. Again, here I didn't use any pipeline. Maybe you can make some pipelines that you do. You one pipeline you standardize your data, another one you didn't. But here I just normally want to show that, but anyway, the code is very small. I don't have to define pipelines. And with the fit method, I train my unsupervised learning method of k-means. Sorry, I made a mistake. So with the fit, I'm scaling my data, and with transform, I'm converting to a new data set. Here, I'm defining my k-means with the new data sets, and also I'm saying that using 3 clusters. After making the k-means object, I'm fitting or training it over my data. Okay, so here I'm training my data and saying that just categorize my data in 3 classes. Let's see what is the silhouette coefficient. Is it minus, positive, or 0? So similar to previous one, I need to import the cluster evaluator. I apply the model over my data, and with dot evaluate over prediction, I can get my silhouette value. Okay, let's see what is my silhouette value with 3. Okay, I think I didn't run here. So with 3 clusters, is 0.61. Maybe you can make a for loop from 2 to 10 and see which one gives you the highest silhouette. Still, it's not negative. So let's make it 4. Now is lower, 0.51. Let's make it 5. It's even lower, Let's make it 2. 0.7. So although we have 3 types of grains, when I use their characteristics, it seems it's better to divide them into 2 groups, not 3 groups. Although I have information from 3 types of seeds, it ends up showing me that maybe you need to just maybe merge 2 of them together and make just 2 groups of seeds. So with cluster center method, you can get the center of the coordinates of each cluster center. So in k-means, it first define centers and then assign the observation to each center. Oops. Okay, I should run here. So look at it, why there is 7 parameters here. I have 2 centers or 2 clusters. Why it gives me a list of 7? First of all, I have 2 lists, right? First list, sorry, second list and first one.
Yes.
But you know, we use 7 variables. Let me go here. This is my columns 1, 2, 3, 4, 5, 6, 7. So I'm working in 7 dimensions. So each point in that each point of my observations have 7 coordinates. If it's in 3 dimension, like xy, it's 2 dimension xy, 3 dimension xyz, 7 dimensions, 7 parameters. So it's the reason, although you had 2 clusters, each cluster has 7 coordinates. And with dot show, you can see the results. Look at the prediction, it's 0 and 1. It assigns a number to each category. So if you have 5 clusters, it would be 0, 1, 2, 3, 4. It's like 6, more than that. So it just means 2 different type of clusters. What can you do, which is not here, it's not possible. You can put the actual label that you had in the beginning and see how your seeds could be renamed. So first I said 2 types of seeds. Maybe you can put a column later and see which one should mesh to which one. So as your next assignment, just change number of clusters and report the silhouette number or silhouette coefficient and tell me which number of clusters is the best based on your silhouette value. So it's a very easy one. You just need to come here, change the clusters and report it. Just make 5.